we're starting the recording for today's class, and we're going to see how different graphs can actually uh, be drawn, especially for the reflection cases. In one of the key uses for uh, ultrasound ultrasound means human audible range is about 20 hertz to 20,000 hertz, and 20,000 it means we human beings are sensitive for to hear a frequency of sound from about 20 hertz to 20,000 hertz. However, kids or little kids have this audible range. As people grow old, that range slowly becomes less, which means we cannot hear as low as 20. Our starting threshold becomes larger than 20 hertz, and our upper threshold, which also becomes smaller than 20,000 hertz. For example, the other day when we were seeing the video from the other channel, I actually could hear up to around 16.5 to 17,000 hertz. I could hear the sound up to that, and beyond that, I couldn't hear anything. So ultrasounds can be used for a lot of different purposes. One of the key uses for ultrasound is to detect defect within materials, and also it can be also used for prenatal scanning. Prenatal scanning means it can be used to see unborn babies inside mother's womb. Ultrasound can be also done for diagnosis. For example, if some person has some tumor or some stone, gallbladder stone within their body, for which case the X-ray is not good enough, or for some cases the X-ray is not recommended, which is the case for an unborn baby, because X-ray actually gives out ionizing radiation, and this can lead to mutation of the cell and might lead to, it's not confirmed, but there is always more possibility with higher exposure of the ionizing radiation that it can lead to cancer or this kind of problems, tumor cancer and this kind of problems. So we can also use ultrasound for this kind of scan. So if I just try to write uses of ultrasound, it's still within your note as well. I might actually turn it up, right? Um, hmm. কি ব্যাপারে ইউজেস অফ আল্ট্রাসাউন্ড গেল কই? আজব। হ্যাঁ হ্যাঁ, আমি তো ইউজেস অফ আল্ট্রাসাউন্ড এখানে নাই দেখা যায়। কি বিপদের কথা। আচ্ছা যাই হোক, অন্য কোন নোট থেকে বাই করে দেখাতে হবে। অ্যাকচুয়ালি এটা তোমাদের বইতেও আছে। There might be another point for number four. If you chose them, I'm going to fill it up over here. But let's just talk about these 3 points for the timing. These are the three most common uses as far as I can remember in my head. Ultrasound scan for medical or industrial cases can be done with a very specific purpose. The purpose is to look inside object without breaking them open or without cutting them open. How do we do the ultrasound scan? We always do the ultrasound scan by means of a probe, and it is usually always done by means of the idea of reflection. In a combined scenario, multiple scan results are merged together to give us a much bigger picture. I'm going to show it to you. And for depth measurement, for example, in the sea, they can use ultrasound scanners to measure the depth of the sea, and also to look out for shoals of fish, so for easier fishing as well. Let me just show you that how does ultrasound scan can work. One of the things that we need to understand that if we draw the displacement versus time, or maybe the pressure versus time, atmosphere pressure versus time for the localized pressure versus time of certain part of the atmosphere, an ultrasound, I mean any sound, can be represented by a sinusoidal wave, for a pure sinusoidal wave from a tuning fork or a single vibrating source. If we have a musical instrument where other devices or other components are added to the main vibrating mechanism, for us we can have some other frequencies involved, and that way we can have a bit of a quality in the sound. But let's say we are not going for that discussion right now. What you need to understand that this much is pretty much what we call one pulse of a sound. One pulse of a sound means actually one full oscillation of the source, which gives out exactly one wave. It doesn't have to be that it should look just like that. I mean, one pulse is basically one wavelength. So it could also be from trough to trough, for example. One pulse of a sound could be also represented like that, starting from here, or it could also represented like that. So crest to crest can be also one pulse. So it's basically one pulse of a sound means one wavelength of a certain wave means one pulse. Whenever we are going to be using ultrasound sources for our measurement, we will be producing pulses of ultrasound, which means we're going to be producing individual broken sound of ultrasound, and we'll be producing them at some gap. So for example, let's say if I use ultrasound source, to get understand it, if I use an ultrasound source that uses sound waves with frequency 40,000 hertz, and the source and the frequency, this is the frequency of sound. This is the frequency of the ultrasound, 40,000 hertz, and let's say the frequency of the signal is maybe 100 hertz. Now, what does this mean? This would mean that if we have a source like that, let's say if we have a source like that, and if we place a detector mechanism, in this case, this can be an ultrasound microphone, which is capable to capture the sound for a much bigger range than the human audible range. And if we feed this sound into an oscilloscope, we'll see the wave that would look somewhat like this. So there'll be pulses of sound, which is going to be like that, let's say. I am not drawing a very zoomed out view. Let's say I'm drawing 3 pulses of sound over here. It can be 4, it can be 5, but whatever I draw over, I should continue this further on. And then there'll be a significant gap. And then there should be another sound. And then should be an equal gap. And there should be another pulse. So the property, this is a highly magnified view of the wave on the x-axis. So this is an extremely magnified view. Let's see, this is the, on the CRO, actually the y-axis gives us voltage, but just for the sake of understanding this, is we are talking about a sound wave, I'm going to write, let's say, atmospheric pressure. The reason these graphs actually look like this is that whenever the source is making the sound, it is making the sound at a 40,000 hertz, and it is making sound 100 times every second. So I cannot actually make a 100 hertz sound and actually make it distinguishable for you for individual pulses. But what it means that, let's say the source makes a sound like, say, ah, and then waits a little bit, and then makes another sound, and then waits a little bit and makes another sound. But because the source can vibrate so fast, it can stop in between whenever it is making the source frequency as 100 hertz. So if I try to elaborate, try to understand, the gap between each of these pulses, frequency of the signal 100 hertz means there will be hundreds of these pulses in 1 second. So from one pulse, I'm just choosing a middle point. I could actually choose, let's say, from the second graph to second graph, this much time gap, the time delay from one pulse to another pulse, this is 1/100 second. Whereas the time delay for within a pulse in between one crest to another crest, which is the actual frequency, which is the actual time period of the sound itself, this much time is going to be 1/40,000 second. So that's the meaning of these two individual different words: the frequency of the ultrasound that we're using for the experiment, and the frequency of the signal, which would mean how often that pulse sound is sent off from the source. So এই জিনিসটা primarily বুঝা লাগবে যে আমরা কি নিয়ে কাজ করতেছি. In many cases, just to avoid confusion, because these pulses are actually really close to each other. These crests are really close to, or these troughs are really close to each other with respect to the gap size that we have. So in many cases, this ultrasound scanning graphs are also shown just by representing one single line. Let's say we draw one line right over here, and the line right over here, and the line right over here. So drawing these kind of vertical lines actually mean that each of these lines represents one pulse. Within this line, we have multiple ultrasound frequency pulses. So if we really zoom into this thing, let's say if we spread it out and really zoom into, let's say within this part, we will definitely be able to find out this kind of a structure of up and down motion. So sometimes this can be given in your question. Sometimes you might only have lines, but you need to understand that these are all meaning the same thing, that we are using ultrasound pulses, which are going to be sent with a certain amount of time gap in between. What's the benefit of this, or what's the use of this? আচ্ছা, ইউজের পার্টটা আমি একটু পরে বলতেছি। let me just make sure এই পার্টটা বোঝা গেছে কিনা, যে ফ্রিকোয়েন্সি অফ আল্ট্রাসাউন্ড আর ফ্রিকোয়েন্সি অফ সিগন্যাল এই দুটো জিনিসের সিগনিফিকেন্স ডিফারেন্স বোঝা গেছে কিনা।
সেকেন্ড ডায়াগ্রামের সাথে ডিফারেন্সটা কি?
সেকেন্ডের সাথে ফার্স্টের ডিফারেন্স কি? আচ্ছা, frequency of the signal মানে হচ্ছে how this is actually I can also write that frequency of pulses. আর আরেকটা হচ্ছে ফ্রিকোয়েন্সি অফ আল্ট্রাসাউন্ড মানে হচ্ছে আমরা কতটুকু ফ্রিকোয়েন্সিতে সাউন্ড ভাইব্রেট করব। মানে আমি যদি জিনিসটা তোমাকে বলি, লেটস সে if I try to make a certain frequency of pulse in my voice, let's say my voice the frequency that I make with my vocal cords has a certain frequency to it. I don't know exactly what that is, but I can actually go by to some website and find that out. That might work. But let's say my voice frequency is, let's say, 10,000 hertz, not that high, I think 5,000 hertz. Let's say my voice frequency is 5,000 hertz, which means if I make a sound continuously, let's say ah, like that, that would mean I'm making continuously 5,000 hertz sound pulses. So individual pulses are placed one after another. So that would mean the voice produced by my vocal cord might as well look like this. So I might have sound that is continuously coming out of my voice. I'm drawing perfectly sinusoidal curve over here because easier to draw and figure, obviously not drawn to scale, there are ups and downs. But if I'm making a continuous sound, this is what we mean by a continuous sound. Whereas if I don't do that, and be careful to make, let's say, a few number of short bursts of sound with equal time delay. For example, let's say like that. This is what we mean by a pulse source, which gives out a sound, waits a little bit, then it gives out another sound, and then waits for the same amount of time as earlier, gives out another sound, something like that. So the frequency of the signal or frequency of the ultrasound pulses, this actually means how many pulses of ultrasound will be given out every second, or how many bursts of ultrasound will be given out every second. So these circles, these are representing one individual small sound. And what is the actual frequency of that sound itself? For example, the frequency at which my vocal cord would vibrate, or the frequency at which the ultrasound source will vibrate, that is this thing, that within the duration for which the sound is made, the ultrasound is made at this frequency, and those sounds are made this many times every second. বুঝা গেছে?
জি স্যার।
Okay, so that's that. আচ্ছা আচ্ছা, এখন এই জিনিসগুলো প্র্যাকটিক্যালি ইউজ গুলো কিরকম? প্র্যাকটিক্যালি হচ্ছে এরকম, we can aim one of these ultrasound sources towards a physical reflector surface. Now that reflector surface can be the bottom of the ocean. That reflector surface could be the inside of a juice canister, or maybe an oil canister, where we cannot look inside, but we would like to measure what is the depth of material within there. We want to find that out. And that material can be a piece of metal, where we want to find out whether there is any crack inside the metal before we install it into our appropriate places, or we want to do some quality check of the manufactured material to find out how much whether there is any crack within the metal as well. So this can be used for a lot of different purposes. Let me show you a few examples. What happens for the sea is, let's say here is a ship, fishing boat, who have ultrasound scanner at their bottom. Sometimes these things are called sonar. Sonar actually is a short form of sound used for navigation and এখানে এসও মানে হচ্ছে সাউন্ড, এ হচ্ছে এন্ড, মাঝখানে আরো একটা ওয়ার্ড আছে সেগুলো আবার নাই। So someone made this abbreviation who is not very, what can I say, good. Sound navigation and ranging. Sorry. So SO makes the so, then N is N, and there A, and then ranging at R. So sonar actually means sound navigation and ranging. Anyway, so this is basically an ultrasound pad which is installed at the bottom of the of the ship, and they can send out ultrasound pulses like that. So let's say I'm going to represent one of these pulses or one of these burst of ultrasounds, one individual pulse, let's say by one curve. So what they do, they send out pulses like that. Now I'm showing these as individual curves, I mean one single curve, but they are not individual wavefronts like the way we have learned earlier. Try to understand that. আমরা প্রথম লেকচারে জিনিসটা দেখছিলাম হচ্ছে from the other channel video is that whenever the tuning fork was going back and forth, it was making a increasing circle which we call wavefronts. In this case, these individual lines are not the wavefronts. Rather, these individual lines which I'm trying to represent are sort of the lines which are these. So if you zoom into these individual lines, you will be able to find individual compressions and rarefactions of the water medium. Actually, I forgot to draw the water. The ship is in water. So that would be available. So these lines actually don't represent the individual wavefronts. Rather, these are the individual gap between multiple pulses of ultrasound. I think I give you the definition of one pulse wrong in the first. Pulse doesn't actually mean one wavelength. Pulse means a fixed number of wavelength. I think I messed up this definition at the beginning. একটু দাঁড়াও। A strong, regular beating or throbbing in rhythmic pulse of the music. The beat resulting from the regular widening of an artery is a medical pulse. In music and music theory, the pulse consists of beats in a repeating of identical yet distinct periodic short duration stimuli perceived as points in time occurring at the mensural level. আচ্ছা বুঝতে পারছি বলবান I actually messed up. Pulse doesn't necessarily mean one wavelength. It can actually mean multiple wavelengths, but equal pulses would be made up of equal number of wavelengths. So if we vibrate the source by the same amount while the source is aimed to make sound, and then we stop it and then make it for the same duration, we should be getting same number of pulse. So point to be noted, these individual pulses can have multiple wavelengths in them, because over here I draw 3 wavelengths in each of these pulses. They can have individually they will definitely be identical to each other for a good measuring experiment measuring mechanism, and they can have more than one wavelength. One pulse doesn't necessarily means one wavelength. Just occurred to me that maybe that definition was not correct. So let's say this sound this device is making this ultrasound pulses from the bottom of the sea, and the sound is coming up coming out, and it's actually spreading out in all directions. I'm only drawing for the lower downward direction because right now I'm about to draw sea. Let's say this is the sea bottom. So this is the ground in the sea. So let's say over here under the sea there is a huge hole or a much lower land. So because soon I'm going to make the boat travel over there. So what happens whenever it sends all of these sound pulses travel through the water, and from earlier experiment, the speed of sound in that medium, I'm writing in that medium because this can be used for in the seawater, this can be used within the human body, this can be used in a piece of metal. So the speed of sound in that definite medium in which we are using that material, that should be known from earlier. Known from earlier means experiment had to be performed for different amount of specimen and average speed of sound through that medium in usually the temperature that the device is supposed to operate at. That is to be known from earlier experiments and should be fed within the device's calculation algorithm or device calculation mechanism as a constant so that we can use it for our calculation. So what happens? The sound goes down and gets reflected off the bottom of the ocean, or we call it seabed, and it's gonna eventually be reflected off, and eventually it will come up and eventually be detected by the same sonar mechanism. Now, one of the key part that typically for sonar mechanisms, the uh, physical object which we use to produce the ultrasound vibrations is also used to detect the ultrasound vibrations. Now, this might sound a little wacky, but this is actually possible. The reason it is possible is that we, I mean, how can I put this? Let me give you a physical example. I'm not really willing to go into the discussion of the silicon crystal, quartz crystal, which is actually used for the detection of sound, for both for the audible range and for the ultrasound range. Have you kids learned about the moving coil loudspeaker in your magnetism or electromagnetism chapter anywhere? Anyone? Do you guys know what that is?
No, sir.
Maybe not. Never mind. Why the same device can be used to both produce the ultrasound and also detect the ultrasound? এটা আমি তোমাদেরকে ইলেকট্রোম্যাগনেটিজম চ্যাপ্টারে গিয়ে পড়াবো। For that আমি জিনিসটা আপাতত এন্টারটেইন করতেছি না, but this is something that you should know. So I'm keeping this question mark in this part. I'm just gonna deciding to move on. So the sound is going to be sent down and the sound is going to be reflected off from the sonar. So let's say this device is going to be operated continuously and this is going to send out these pulses every once in a while, and that once in a while will be recorded. So here I'm actually drawing a lot of different multiple different waves over here to give you a little bit of an idea how this sound is actually made. But in practical cases, they usually don't send out this many waves for a certain thickness of C. Ideally, what they always prefer to do is to send one pulse, receive its reflection, and then send another pulse. I'll tell you why that is important. Now, one of the key part, whenever this pulse would be sent, let me just consider that there are two different things over here. Let's say we have one sending mechanism of sound over here. So this is the source of the sound. And right beside this thing, let's say we have a microphone kind of object. Let's say that's called receiver. So these two things are just placed side by side. The source or the blue thing is going to make the ultrasound pulses, and the R or the red thing is responsible to receive the ultrasound pulses, and they're placed pretty close to each other. So what's going to happen whenever this source will make the ultrasound, it will be almost immediately received by this one. And let's say it makes one single ultrasound pulse. So all of these individual pulses are not here. Let me erase that. Okay, let's say this source is sending down one specific pulse. So it is producing one pulse, and that pulse is going through the seawater. And as it will go down, it's definitely gonna become spread out. So it's gonna reflect off the bottom of the sea, and eventually it's gonna reflect back to the boat. And as a result, a very small fraction of the sent out energy will be actually be received as the reflection or echo. This is a very important aspect, that if we send out a very powerful sound, the echo that would be heard after the reflection of the far objects, that would have a much smaller energy amount, or you can say the loudness of that echo would be pretty small, or the amplitude of that sound of echo would be pretty small compared to the original sound. So the way this sonar mechanisms work is that we have an oscilloscope. Let's say this is an oscilloscope. This is an oscilloscope screen. Or on the y-axis, we usually have the voltage on the y-axis. So let's say we have the voltage. I'm just writing for a good oscilloscope. I can write voltage, or I could also write pressure over here. because that's how the ultrasound actually affects the localized pressure of the water medium. Or let's say I'm writing voltage versus time. So the way it's going to work, whenever the source will produce a single sound, ultrasound pulse, this red object, which is a receiver unit, will immediately detect that sound. So it is gonna, let's say it detects the original sound of the source, which is drawn, let's say by only one pulse. I'm only show you one pulse, which is not very realistic, but let's say only one pulse. This sound, this one, the sound goes down and reflects off the ground of the bottom of the sea, and eventually reflects back and is received once again by the receiver. So that received sound reflection is going to look somewhat like this. It would have the same shape, same frequency, but it will be significantly smaller in amplitude. There's a difference. So how much time should it take for the sound to travel? How much sound should it take for the sound to travel from the bottom of the ship to all the way to the base of the sea and eventually come back? This is the amount of time that the sound would take, the time amount that is between these two pulses. So this is our send pulse, and this is our received pulse. With the appropriate scale available in the CRO machine, cathode oscilloscope, we can measure how much time is that. Let's say this time is t, and measuring this time is practically what we want to do out of all of this discussion, because then speed of sound can be measured by twice the depth divided by t, or d can be measured, d equals to vt divided by 2. So that's basically how the machine operates. Now, usually it doesn't actually send only one pulse, because one single pulse might actually get lost. So what the device does, it keeps on sending that same pulse using a certain amount of time delay. So what this means, that the machine keeps on sending a certain frequency of ultrasound, where the frequency of the signal itself, this can be operated, or this can be changed by the operator in the sea as per their requirement, which means they can control how often the pulses should be sent. And usually for a regular device, this pulse is usually fixed. Some high-end devices, for example, in the army, or not in the army, in the navy, some navy ships can actually have, or some high-end submarines, they can also have devices which can change the frequency of the sound as well. But what is important, that whenever the ship would actually travel to a much deeper water, let's say the ship travels from here and is going over here, and let's say the ship comes up over here now. So what's going to happen at this point? At this point, the sound is going to take, one send pulse is going to take a significantly longer time to go hit the bottom of the sea and eventually come back to the ship once again. So this is going to cost us a much longer time. Now, this might lead to some confusion sometimes, because usually whenever we use the sonar in, let's say, this case, there is a certain time delay that the operator can choose, at which they're going to send all the send pulses. Let's say this is one send pulse, and this is one of the received pulses, and then let's say we send another pulse of sound from the source, which is received, let's say, right around here, and then the cycle continues. So we're sending one pulse and we're receiving the reflection. So the idea is that this is send pulse 1, this is receive pulse 1, this is send pulse 2, this is receive pulse 2. So this is the actual amount of time it took for the sound pulse to get to the bottom of the ocean, get reflected off the seabed, and eventually reach back to the receiving unit of the sonar mechanism. So that gives us a perfect measurement of time. What is really, really important, that we cannot send our second sound before we receive the first reflection. Hear me out on this one. The machine should not send a send pulse before it receives the earlier reflection. This is going to lead a significant error in measurement. I'll show you why. Let's say the ship is traveling from here to deeper water, and for some reason, let's say the operator was not very careful, or they didn't have earlier data within their grasp, so they did not change the frequency of the signal as the sea traveled from a bit shallow sea into the deeper sea. So what's going to happen in that scenario? Let's say they're going to keep sending this same pulses in the exact same frequency. This is how it's going to work out. There is one send pulse. This is another send pulse. So the send pulses are sent at the exact same frequency. But now each reflection, actually all the send pulses should have the same amplitude. I am messing up with the amplitude a little bit, but all the send pulses should be identical. But now the received pulses will start to come after a significant delay. So earlier, for this amount of water, let's say this was the amount of time it took for one pulse to go to the bottom of the sea and eventually come back up. But whenever the ship actually travels to a deeper water, the amount of time requirement would become significantly longer. So let's say what is happening right now, this pulse or send pulse 1, S1, will be received, let's say right around here. Let's say I'm gonna write it in a random place, let's say right around here. This send pulse will be received right around here. It's possible simply because the depth of the sea is now much bigger, so it's simply taking longer time. But this might lead to wrong observation, because what happens, the cathode oscilloscope device actually does not show you from the very first signal. It keeps on sending the signals and keeps on receiving the signals, and based upon what this receiving unit, this red dot over here, the cathode oscilloscope is actually connected with this receiving unit, and whatever this receiving unit receives is fed onto the screen in real time. So whenever the sending unit actually sends out a pulse, it actually keeps on sending the pulse at a fixed rate, let's say 100 times per second, or maybe 200 times per second, or maybe 10 times per second, depends upon the device. And the receiving unit receives all of this sound from the source and also for the reflection, and puts them on a certain display in terms of that this is the instance of time where the original sound was received, which is shown by a much bigger amplitude, and then this is the instant of time where the reflection was received, which is shown by a much smaller amplitude, but the frequency remains the same, the shape of the sound also remains the same. If the sea is deeper and these sound send pulses are not spaced out, then the operator is going to see all of the figure that looks like this, and within the display these things are not labeled like this. I have labeled these circles over here for you to understand, make sense with you, which means this is the reflection of this one and this is the reflection of this one. But the operator is simply going to see an up and down figure like that. So they're going to see large pulses, they're going to see short pulses, they're going to see large pulses, short pulses, and as per experience they'll consider that this is the send pulse and the next one is the received pulse, because that's usually how it works, because this is usually how the device works. You send a pulse and then you receive the receiving pulse, which an in between gap gives you the time amount for the echo to go by. But this is actually not true, because in this case this was actually not the time the sound took to travel to the bottom of the sea and eventually come back up. The amount of time it actually took was over here. The reason this mistake is happening is because we are sending each pulse before receiving the earlier echo. So what is really important, as the ship travels from shallow water into deeper water, we must space this out more. Now space this out, actually what I'm meaning, physically spacing out on the graph actually means that we must send out the send pulses with a bigger time gap, which means each send pulse should be sent after a longer time delay. For example, if we are sending out these pulses over here, let's say if this was for 100 hertz, maybe we should so maybe whenever we are traveling to a deeper water, we should actually prefer to send it at maybe 50 hertz, because if we send it at a 50 hertz, what will happen, this wave would not be there, this send pulse would be missing. We have this wave, we are going to wait double the time, so we're going to miss out this pulse, and we're going to send another pulse over here. Then we are not going to get then we're going to get the reflection of this sound right over here, and this reflection would not be here, and this send pulse would not be here either. Rather, after a really long delay, we're going to get this reflection, which is for this wave, and then we're gonna send out another send wave just like that. So by sending out the pulses with a longer delay, we can avoid the confusion that the sea is actually shallower, or the measurement of time for the wave to travel down and eventually come up. That mess up can be avoided. এই পার্টটা কি বুঝা গেছে?
জি স্যার।
প্লবান?
জি স্যার।
This another type of wave, similar type of wave can be also, similar type of oscillation graph can also be used for measuring, for detecting errors, not errors actually, manufacturing fault within a piece of metal. Another example can be like this. Let's say this is a piece of iron block for which we want to see whether this object is perfectly flat or not, or whether there is any crack in between. If you wonder why should it have crack, I mean, objects can have crack because of physical torsion, or they can have over a long period of usage. So from earthquake, or let's say from poor manufacturing. Let's say this is one of the slabs of the side hull of Titanic ship. They had so many internal cracks, and that's why, and they were so much brittle, that's why it actually got down so fast. So many parts actually, other than bending, they actually cracked open like biscuits or crackers, and the disaster happened. Anyway, let's say this is a piece of iron block. So you're seeing the side view. Let's say we have put this on a piece on a table. This is our table, and we have a ultrasound probe. An ultrasound probe is basically a device which has an ultrasound source on it, and within this head, or within this probe, we have the send and the receiving units installed simultaneously. Pretty much similar, not exactly same, pretty much similar like what I showed you over here, that we have the send and the receiving unit placed side by side. So what is going to happen, the source is going to send ultrasound pulses, and the receiving unit is going to receive them. So the send pulses would be picked up by the receiver almost immediately, because they're really close to each other, and then the sound should travel down, reflect off the bottom, reflect off the bottom, and it should eventually reflect up. And this CRO with which this probe is connected, this would be able to give us the view of that. So if we have no crack within the iron piece, we might actually get a clean looking reflection graph. So let's say this is our voltage, this is our time. So let's say for good iron piece, this is our send pulse, and this is our reflection. I'm going to draw it 3 divisions apart, and let's say we send another send pulse after 2 more divisions. So we are sending the send pulses over here. Do you kids actually see the small dots of the whiteboard? I mean, do you kids see small dots on the screen?
Yes sir.
এটা দেখা যায়?
জি স্যার।
Oh, okay, that's very good. Let's say I'm using let's say all the send pulses are sent, let's say 5 division apart on the whiteboard dots, and the reflection is received at 3 divisions. So as long as this piece of iron, which has a uniform thickness all over, so the thickness of the iron is considered same, it doesn't have any problem. So what is happening? The sound is going by, is reflecting over the bottom surface of the iron and eventually coming up. So we should have all the reflections showing up by the same variation over on the receiving end. That is more likely to happen. So send pulses, and actually I messed this one up. Like that. এরকম হওয়ার কথা. Now, let's say there is a crack on the within the piece of the metal. Let's say somewhere over here. Let's say the crack is, I'm intentionally not putting it at the middle. Let's say the crack is over here. There's a crack inside the metal which is not visible from the outside. What is going to happen in that scenario? Whenever we'll bring the probe right over here, the ultrasound pulses are going to reflect off this crack's top surface and eventually go it back to the probe. It is not going to be traveling through the crack and eventually rise up. And this would take a significantly smaller time. The part that I need you to understand, time it takes for the ultrasound pulse to travel all the way thickness and eventually go all the way up would be longer. The time it takes for the ultrasound pulse to travel shorter distance and eventually go up by a shorter distance would be smaller, which means if you do have a crack in any place within this metal block, other than the regular reflected pulses which was obtained for most of the part, you're going to suddenly have for one location a much closer reflection, and that closer reflection should be longer in size because it's going to have a little bit more amplitude because it did not travel as much medium. For example, if this whole thickness is, let's say, 10 centimeter, that would mean that each of these original reflections, they had to go through a total of 20 centimeter of metal medium, and they underwent a certain amount of reduction. Whereas if this crack is, let's say, 2 centimeter above this surface, which would mean they are 8 centimeter below the top surface, this would mean these green waves, they actually had to travel by 16 centimeter, which is a bit smaller compared to the original reflections or full reflections of 20 centimeter, which means they will have a little bit of less reduction. The amount of length that a certain wave travels through a medium, the more it is, the more energy it loses to the medium particles, the less distance it has to travel through a physical medium, the less distance, the less energy it loses. So if the reflection is received a bit earlier, we're going to have a bit longer amplitude, but this will be definitely smaller than the send pulse. You have to understand that send pulse will always be the biggest because it's received almost immediately by the receiving unit in the probe. So that's what's gonna happen. So, and obviously you should understand that whenever we have the fraction over here, this sudden appearance of a new pulse within our screen actually proves on to show that this metal might have some not might, it does have some problem or cracks within this metal piece somewhere at a certain length. And by measuring this time, how much time is this, we could actually appropriately find out where this thing is, where this individual crack is located. So that's also another industrial process to use ultrasound for our purposes. The other example, the other use for ultrasound mechanism is for prenatal scanning or neonatal scanning, not neonatal scanning, prenatal scanning, yes, prenatal scanning, or just to take a scan of the unborn babies within mom or about to mom, pregnant woman. The way that mechanism works is actually pretty interesting. I'm going to show you a little bit of cross-sectional view for that. That is also done by merging the information of a really large number of direct scans. So let me show you what it means. Let's say this is a pregnant woman, a standard pregnant woman, figure not drawn to scale. No offense to any pregnant woman, this is just how I draw. Let's say try to visualize the cross section where the baby is. Let's say the baby is inside here, figure not drawn to scale. Let's say this, I'm going to try to show you the cross section of this picture over here. Or should I show you long section? Actually, I could show you the long section. Yeah. No. Diagram. Yes, got it. I'm looking for this diagram. Okay. Yes. How big is this image? Pretty small. This one. Yeah, workable. So what happens? Okay. No. Okay. Yes. I cannot flip this. Can I flip this? No, I cannot flip this. Acha. This orientation will work just fine. No big deal. So let's say this is the person and we are about to take a scan of this baby. So the way it works, let's say we're going to place the ultrasound probe, which also is used with a certain amount of coupling jelly so that the air cannot produce much of a problem for the scanning right over here. The way this mechanism works, it actually sends out one pulse of ultrasound that travels to the womb, to the baby's body, and travels all the way back to the backbone of the mom. It comes all the way back reflected to this part. So what you need to understand, if I show you the cross section of the person, this is actually the long section where the baby is not long section, the person is long section, the mother is long section over here. If you consider the cross section of the body, so let's say this is the central bone, which is this one. Let's say this is the bone, and here is the rib cage, or no, rib cages wouldn't be there where the baby is, so forget the rib cage. So, and let's say this is the whole belly structure, and let's say this is the uterus and this is the baby. So this is the bone, the backbone, or we call it the centrum of the whole vertebra. So the idea is for this whole scan to be successful, this probe needs to be aimed by the expertise of the technician or the nurse. This thing needs to be aimed towards the backbone. So any single time this thing is rotated to another location, they're not trying to aim it towards the baby, rather they will try to aim it towards the backbone, because within this whole structure, this backbone is the most stronger reflector. So what is done, sound pulses, ultrasound pulses are sent through the body, and that goes to the baby, and whenever it changes through a medium, for example, let's say the moment it changes from the fat muscle to the tissue, and then from the tissue inside the uterus wall, and then to the amniotic fluid, it goes into the leg of the let's say in this case for my line, it is passing through the leg. It passes through the leg of the kid, and then from there it goes actually through goes out of the leg. So each time the ultrasound pulses actually undergoes a medium change, so it goes from one type of tissue to another type of tissue. It makes a bit of reflection from the surface. That's how any wave actually works, which you might have seen in your earlier figure for the first chapter, that if we have two different medium A and B, and if we send a little bit of wave or energy onto their surface, a portion of the wave always reflects off, another portion of the wave actually enters into the second medium. And this is what happens. So if this is 100%, and this is X% and this is Y%, logic tells us that by the law of conservation of energy, that X% plus Y% would always give you 100%, which means the total amount of energy is divided into two parts. One part is reflected off to the first medium and the other part goes through. This is basically the mechanism by which this is done. So whenever the ultrasound pulse actually goes through, it actually reflects off from different parts of the baby and different parts of the mom with different amount of time. So what this actually means, that if we try to pick up the reflection of one cent pulse, I'm saying one. So let's say this is the voltage versus time graph of the oscilloscope, and let's say this here is only one pulse of the ultrasound cent pulse. Let's say whenever it goes through the belly, it gives a small reflection, which is pretty large. Then as it enters into the baby, it gives another reflection. As it leaves out of the baby, it gives another reflection. As it comes reflected off the bone marrow or the actual bone, the backbone, it gives the last reflection. So from one single pulse, for multiple different medium changes, we can have multiple different vibrations. Now the device that we use, this is how this would look like in a single time-based oscilloscope. This device sends out a lot of these signals within a single amount of time and measures all of these individual sounds, and it then from the algorithm or from the software, it determines which are the pulses which are relevant for the baby. It then crops those out and highlight those individual time values, the time value locations for the baby position in different black and white color. So let's say they're going to represent all the pulses received for this much time, not white. Let's say this machine, by its software, by its design, is going to represent all the reflection received over this much time as black, and it's going to represent all the reflection received within this much time represent as black. Only the reflections received within a certain fraction of time, which is for which there is a typical ideal value, usually exactly it goes on to show that at which location the baby is located. For example, the baby is located within this much space, actually within this much space. So the probe is going to give us the reflection value for all of them, but the software is going to discard all the other reflections other than a very specific time amount, and those specific reflections are going to be displayed on a two-dimensional screen as white pixels, and non-visible locations will be represented by dark pixels, which ultimately give us this black and white figure like this. So you can see that it's almost non-understandable what's going on. For example, over here, I can have a look that this is actually a pretty nice view. So this is actually the whole womb, and here is the placenta coming in. This is the leg. This is sort of like the human brain. The baby's brain is almost developed, and this is not a totally developed embryo. Baby is still an embryo, so not quite developed yet. So that's the whole point. And one thing you should see, that in all of these figures, you should see that these figures are sort of like a cone shape. Do you see that? They are not actually a flat image. Do you see that there's a cone over here?
Yes, sir.
The reason the cone is over here, because these images were actually made in a mechanism like this radial scanning. So the probe was actually aimed towards the bone, and the image was taken off for a small portion within that conical shape. And that conical shape within which the baby existed is actually shown over in this image. That's how the prenatal scanning works. It is also extremely dependent on the idea of ultrasound scanning. The reason we prefer to do ultrasound scanning because X-rays for unborn babies is not a good idea. And also ultrasound and also one more thing you need to understand. You don't have to actually write about this pretty well, but I need you to understand that in the process of a prenatal scanning, for example, situations like this, the device actually receives a good number, a really large number of not only one reflection, rather it receives multiple reflections for the same ultrasound pulse. It then picks up on the relevant images from the programming and discards the non-relevant reflections, and then puts all of those relevant reflections in a black and white space. And that black and white space ultimately becomes the ultrasound image. এই হচ্ছে মোরলেস আল্ট্রাসাউন্ডের ইউজেসের কাপচাপ। আর হচ্ছে আমাদের লাস্ট একটা পয়েন্ট বাকি আছে, আল্ট্রাসাউন্ড ক্লিনিং। আল্ট্রাসাউন্ড ক্লিনিং এর বেসিক আইডিয়াটা অ্যাকচুয়ালি খুবই সিম্পল। Ultrasound cleaning, the key idea behind ultrasound cleaning is that we have an object which is submerged within a fluid medium, and that fluid medium particles are vibrated from an external source at an ultrasound frequency for a significant duration of time. The object which is placed within then is also vibrated by their frequency. So if the object has some difficult to remove kind of dirt or grime, for example, ornaments which have gone which tarnished over long usage, if you place them within that solution, you need to have appropriate certain material within the solution as well for the whole thing to work. I mean, only water might not work in most cases. And then if you turn on the ultrasound device, the basic idea is that the ultrasound vibration is going to vibrate all of those medium particles, which is basically going to work like a rubbing off, or something like hose pipe দিয়ে should I use this example? No, not a good example. So yeah, actually the vibration of the ultrasound is going to cause the medium particles to vibrate back and forth very vigorously, which is going to rub off the dirt and the grime of the object. There's a pretty nice video for this. I'm going to share the link of that YouTube video in my video description for this ultrasound cleaning video. You can have a look around it. There is actually a channel which is built around an ultrasound cleaning device. These videos are actually pretty what can I say, peaceful, no, satisfying videos as per the internet meme thing goes. So yeah, ultrasound scanning is pretty simple, but the other parts is a bit technical, which I tried to give you the idea for. বুঝা গেছে কি আজকে ক্লাস? We don't have much time, so I'm not sure if I can take questions, but if you have any question, write them down. I'm gonna entertain those questions in the next class, inshallah. ঠিক আছে? বলবান?
Yes.
আচ্ছা, আসসালামু আলাইকুম।